Well, ladies and gentlemen, welcome to the last talk in the Geology lecture series this year. As you all know by now, for the most part, this lecture series wouldn't be possible without the financial support of Oregon Resources Corporation, also the college. Also, one of the added benefits that we started last year, and thanks to the guys in the tech booth, Dallas and Floyd and Dean, that are allowing this to be a live web stream. So I know that we've regularly had folks down in Gold Beach that they used to come up here with a group of 4 or 6 or 2 or 8, whatever Dick Bateman could actually get convinced to make the trek, and now they get to actually watch it back home. Now, I'm not suggesting that next year all of you watch it at home either, because there actually is something just like music about actually physically being in a particular location. But again, without Oregon Resources, the college, and for this evening's speaker, the Ocean Leadership Consortium, we wouldn't be able to put on these spectacular free events, and also without all of you showing up on a regular basis as well. So thank you all for taking time on an incredibly beautiful Saturday to show up here. If you didn't sign one of these little sheets when you came in, if you take a minute at the end to sign as you go out, because part of it is getting people, as far as some of the different organizations, to send folks out to the edge of the known world on the cutting edge here, and justification is always a good thing. It's my pleasure to introduce to you this evening Dr. Demian Saffer, who comes to us as an Ocean Leadership Distinguished Lecturer. And there's about 45 talks in their series this year, split among 6 research folks that have been working in the ocean drilling program. We're actually the only 2-year institution to host one of these talks, which I take some significant pride in, and also great appreciation for Demian for flying cross country from Penn State University, where he's currently on the faculty, to participate in their lecture series this year. Demian grew up in the East, went to Williams College as an undergrad, and in wandering around our backyard today, one of the things that he had an opportunity to do fairly early in his career was to do a little bit of research, actually research for a senior college bachelor student, which then probably became another project for himself, and then graduate school and so on. Went and did his PhD at UC Santa Cruz, started teaching in Wyoming, and has been at Penn State for several years, part of the ocean drilling program, and you'll see a little bit about that tonight, including a couple images of their new drilling ship and platform, the Chiku, which is just amazing in and of itself. He's been recognized for both research and teaching by GSA and a couple of different organizations, and so without further ado, it's my pleasure to introduce to you this evening Dr. Demian Saffer.
Well, thanks, Ron, and thanks everybody for coming. Although it is a lot of time to go to all these places and visit and give talks, I actually really enjoy it. It's a great opportunity for me to talk to lots of different people and hear about exciting things that are happening, including a wonderful private field trip today that I got some pictures, crappy pictures from my iPhone, but pictures nonetheless, that I'll show you today. So what I'm going to talk about today is basically what this title implies: drilling into plate boundaries, particularly subduction zone plate boundaries. It's the same kind of plate tectonic boundary that exists off the coast of northern California, Oregon, Washington, and Canada, as well as the type of plate boundary that spawned the giant earthquake and tsunami that I'm sure everybody's heard about in March offshore Japan. Before I do that, I did want to jump in a little bit to talk about the ocean drilling program in a more general sense. And so I'll start with that. Before I leave this slide, there are a couple things I wanted to point out. This fuzzy picture in the background, that you might be able to sort of see this crusty looking thing here. The reason it's fuzzy is that this is a photograph that was taken at 13,000 feet beneath sea level from a submarine. And this is actually the living, breathing plate tectonic boundary. This is the trench right here, offshore Central America. And so this is a subduction zone plate boundary. Here we are on one tectonic plate of the Earth's outer shell, and here we are on the overriding plate. And it's a calcium carbonate crust that marks that boundary, where you're on one plate and you can literally put your finger, well, you can put the robot finger of the submarine on that plate boundary. And then here is a photograph of some rocks that were at one time at 15 kilometers depth beneath the surface in a subduction zone plate boundary And this is what we sort of envision the rocks would look like if we could access them at those depths below sea level, below the seafloor. The last thing I should mention here is that before I launch into my talk, what I'll be telling you about is work that I've been heavily involved in. Some of that work is my own or my students, but much of it involves many, many collaborators, including graduate students, colleagues within the US, colleagues in Europe, Germany here, my colleague Achim Kopf, and many, many others. So hundreds of folks who are involved in this. And of course, the work wouldn't be possible without the support of the Ocean Drilling Program. And then my talk today is supported by the Consortium for Ocean Leadership, which is the United States part of the support program that lets scientists like me go out on the drill ship and do the work I'll tell you about. All right, so before I jump in to tell you about this, what I think is a pretty exciting, ambitious project to drill into earthquake-generating fault zones, thought I'd tell you a little bit about the Ocean Drilling Program more broadly. So the Ocean Drilling Program has been around for upwards of 40 years now, and it basically is a scientific, a major international scientific program. Over 20 countries are involved and contribute both money and human resources to operate 3 different drilling ships that go around the world to study all kinds of problems, including climate change, to understand what's happened in Earth's past and what that might mean for climate change in Earth's future, to study a vast sub-seafloor microbial community that may have as much biomass as exists as we know it on land, to study the formation of the ocean's floor that paves 2/3 of the planet, and of course, to study earthquakes, the thing I'll talk about today. This program, one of the main things that they do is we collect core samples, and this is a photograph of 3 sections of rock core or sediment core. They're about 3 inches across, and that's one of the primary things that we get to study from the drilling is a continuous record or continuous samples of the Earth's subsurface. Now, when I first saw this issue of Life magazine, I got a reprint of it from 1961. I was really excited because it's not very often that scientists are in the news, and when we are, it's never for something good. It's usually for something like the scientists in Italy who are now on trial for manslaughter for failing to predict an earthquake. In our case, we were very excited to see this because this is actually documenting the 50 years ago, the onset or the birth of the Ocean Drilling Program as a major scientific endeavor. And this was what's called the CUS-1 project. It was the first time that scientists got together and convinced oil companies to fund a drilling barge. It was basically a barge retrofitted with a drilling stack here to drill into the ocean crust and see what's down there. And I don't know how many of you can see this right here, but the other thing that's pretty cool is I've never been interviewed by John Steinbeck, but this was back in the day when geologists were real men and not weenies that sit in front of computers like me. So this appeared in Life magazine in 1961, and I don't want to say we've come a long way, but I'll say that the major project I'll be telling you about today is called Nanosize. It stands for the Nanchi Trough. It's an area offshore Japan. Seismogenic Zone Drilling Project. So it's to understand earthquakes or seismogenesis, and we've chosen offshore Japan for a few reasons I'll tell you in just a minute. We also got some media coverage. This is a major spread in a major circulation Japanese publication here. Pictures of the drill ship, pictures of drill bits. And it came out in November 2007 as we were embarking on the first journey as part of this multi-year project. Now this was no Life magazine, this was Playboy in Japan. And I don't know if that's a good thing or a bad thing. I will just say that I think Playboy is a different type of magazine in Japan than it is in the US. And the way the Ocean Drilling Program works is there are 3 vessels that are basically funded to be out there and do the best science, and then scientists like me or like Ron or others propose to get time on these ships, use these tools to do projects that we think are interesting. And one cruise will be 2 months of time on one of these vessels with a complement of anywhere from 15 to 30 other scientists who are all cooperating and living together for 6 weeks to 8 weeks and drilling. The 3 platforms are what we call a riser drilling platform, the Chikyu. This is the newest addition to the fleet. It's run out of Japan, and it's the one that we use for the project that I'll be telling you about because it has unique capabilities of a special type of drilling called riser drilling, which allows deeper penetration into the subsurface so that we can actually access the zones where earthquakes happen. The JOIDES resolution is the United States contribution to the program, so the US runs this ship out of Texas, and it's been going for, this ship has been running for over 20 years. And then the European Union supports what are called mission-specific platforms. So these are specialized platforms for drilling, or ships for drilling. For example, if you need to go into the Arctic to study the sediments under the Arctic Ocean, you would need an icebreaker. And for that, there are sort of these specialized vessels that are one-off operations. They're not continuously operating like these two ships, but they would hire or rent the ship for 8 weeks to go do that project. So it's kind of a three-legged program, if you want to think of it that way. And the CHICU is the leg that we use primarily for the earthquake studies, again, because of its capabilities for drilling deep into the subsurface with this riser drilling technology. And the limit right now, in terms of the amount of pipe that's on the ship and the technology that's available, is about 4.2 miles or 7 kilometers beneath the seabed. And this could be done in up to 2.5 kilometers of ocean depth on top of that. So we're talking about getting down from sea level down to about 6 miles or 10 kilometers into zones where earthquakes are actually popping off. Just in terms of the scale of the vessel, Ron mentioned it's a pretty amazing ship. To be able to access or run the drill pipe down to those depths, the drilling derrick here, just as a sense for scale, is 112 meters or about 380 feet above the water line. This is a helicopter pad. But what you might not be able to tell is this will land a 14-person Bell helicopter, the kind that are used for Coast Guard rescue. So this is basically a giant deep water drilling platform. And this is a photo that those of you who've been around a while might have seen. This was during the construction of the vessel. This is actually not the main propeller of the ship. This is one of 6 thrusters that are used just to hold the ship in position while it drills. So there are 6 of these. They're the adjusters. They're not the main prop. And these are Kochi University undergraduates for scale. Now, one of the other things, I think this movie's not going to work unless I come out of movie playing mode here, or come out of PowerPoint mode. But one of the other things about riser-based drilling is that you need to have the ship very still. In other words, you can't drift off from your drill site down below you, or else you'll shear off and break the pipe. And so the technology just involved in that is amazing. You need to have a very stable platform. And the analogy I like to use with my marine geology students is that if you were to look at me from the waist down, what we're talking about is me holding a piece of dental floss, or something about half the width of a piece of dental floss would be the drill pipe, from my waist to the floor to hit something that's the size of the head of a pin. And through that time, the drill ship has to stay put to within 0.5 millimeter. So that's the kind of precision we're talking about. With ocean currents like something similar to the Gulf Stream, plus winds, plus wave action, the ship has to constantly be adjusting and burning fuel, for that matter, to stay put. So that requires a lot of stability. And so this, again, apologies for the coming out of PowerPoint mode, but we're looking at a view onto the CHICU out in the open ocean from a 130-foot barge that's delivering supplies. So the 130-foot barge is moving pretty well in the seas, and the CHICU just kind of looks like an island. And I guess the one other thing before I launch into talking about earthquakes, that's sort of the claim to fame, in a sense, for the CHICU, is that, or a new claim to fame, I should say, is that on March 11th, 2011, when the major earthquake and tsunami hit northern Japan, the CHICU was actually in harbor in northern Japan, getting ready to go out on a drilling cruise. What's typical when the ship is in port is that it's a great opportunity to have the public come and tour the ship and see what all happens on the ship. And so that was going on. There was a tour, a major tour that included a group of elementary school kids. So 42 elementary school students and 3 teachers were on the ship when the magnitude 9 earthquake happened. And due to a combination of luck, but mostly quick action and quick thinking by the ship's captain, they were able to get this 725-foot vessel, heave anchor, and get out of port, not far enough to avoid any damage, but out of port to serve as basically a rescue vessel for the dock workers who were preparing the ship for its voyage, and the elementary school kids and the teachers. And so in addition to being a drilling vessel, it's also a rescue vessel of sorts, I guess. Okay, so on to earthquakes. I basically put this talk together with the assumption that I'd have a pretty broad audience, including some people who don't know a lot about plate tectonics or subduction zones or earthquakes. So I'll try to run through this relatively quickly, but hopefully clearly. What we're looking at here is a map of the Earth showing the ocean's bathymetry and topography and color. And then all of the earthquakes over the last roughly 100 years are shown here as the dots. And what you can make out pretty clearly are the plate tectonic boundaries, the Pacific Ring of Fire here, These are the subduction zone plate boundaries, California and the San Andreas. You can also make out the mid-ocean ridge systems, which are typified by smaller and generally shallower earthquakes, these orange guys. And then other major subduction zones in addition to the Ring of Fire. For example, here's Sumatra. So this was the location that spawned a magnitude 9.2 major earthquake just after Christmas in 2004. And one of the things that we worry about when we talk about earthquakes and subduction zones in particular is how big the earthquake can be or is. And to a large extent, the size an earthquake may be is determined by what we call the size of the seismogenic zone, or the size of the region along the fault zone that can break in the earthquake. So a bigger area that breaks, you can have a bigger earthquake. And that's governed in turn, if we think about the subduction zone here, so here's the plate of the Earth's outer shell that's subducting beneath the continent, the overriding plate. So this might be the Pacific Oceanic plate, and this might be the Cascades here. There's what we call the width of that zone, which is from the shallowest depth where the rupture or the earthquake starts or can move things, down to the down dip edge of that, so the width, and then also the length along the margin, say from Seattle down to Southern Oregon, for example. And so it's that area or that size that in part governs how big an earthquake might be. The other thing that's important is how much the fault moves. Does the top move relative to the bottom by 10 feet or 100 feet? And here's just an image to give you a sense for when you have very large, potentially devastating earthquakes. This one is a photo of downtown Anchorage after the 1964 magnitude 9 event. These are sort of the largest events, most massive events that we know of in terms of energy release and damage. And the magnitude 9 earthquakes, what makes them magnitude 9 and not 7s or 8s is really this area, the size of the region that breaks. Now in more detail, so again, this just kind of restates what I've just said, it's the dimensions of the seismogenic zone that are our biggest control on earthquake size. And that's kind of shown schematically, so zooming in now just on this front part of the system where we think earthquakes happen, that's shown here. So this would be what we think of as the seismogenic zone. So between earthquakes, this is sort of welded shut or locked together, and it stores up energy like a spring would. And then it releases that energy when the stresses that have built up exceed the strength of the rock. It suddenly breaks. I say suddenly, that means that it may take 1 to 2 to even 3 minutes to finish moving. But energy that's been stored up over a few hundred to 1,000 years will be released in a matter of seconds to minutes. And I've kind of schematically shown that seismogenic zone ending here at this shallow depth, but we actually don't really know if that actually extends all the way to the seafloor here, or perhaps if other fault zones branch off of the main plate boundary, break through the upper plate, and accommodate earthquake motion. This becomes very important when we think about tsunamis. Something like this would very efficiently move the seafloor up and down, and that's what triggers a tsunami or a major ocean wave. And so understanding where the system can slip in an earthquake and whether that branches up here or maybe branches out to here becomes supremely important for understanding the risk of tsunamis in terms of how big and where they may be generated. The final thing that's worth noting on this particular cross-section image is, in addition to the seismogenic zone, one of the big new discoveries about earthquakes in all kinds of plate boundaries, but in particular in subduction zones, is that we see all kinds of what we call weird behavior. So instead of just normal earthquakes, if you go just above, shallower, or just below, deeper than this traditional earthquake generating zone, we see weird, slow earthquakes that don't have as much high-frequency energy. In some cases, they're just like fast creeping events, but kind of unusual and different fault behaviors that may be related to building up stress in the seismogenic zone where major earthquakes happen. And so part of drilling for us is to understand not just where and how the seismogenic zone behaves, but also to understand these weird behaviors that may be linked to the seismogenic zone and major earthquakes. Now, just to give you a sense for why we work on subduction zones as opposed to, say, the San Andreas Fault, which is probably the most famous fault zone on the planet, it's really that when you think about the energy that's released in earthquakes, subduction zones account for basically all of it. And so that's this pie chart here. It's a little bit cut off, I guess. But this is 100 years worth of earthquakes from 1906 to 2005 shown here. It's the energy that's been released, or moment that's been released in those earthquakes. And the purple here is subduction zone earthquakes. And this is everything else, including the San Andreas Fault. Now, we can also think of that a little bit differently and say, okay, so subduction zones are important. But it's not just that, it's that the big earthquakes in subduction zones are even more important. And so if we look at earthquakes from the last 105 years, from 1906, including 2011 and including the recent Japan earthquake, that's this pie chart here. And what we see is that if we take all of the magnitude 6 earthquakes that happened in the last 100 years or so, that's this wedge of the pie here. All of the magnitude 7 to 8 earthquakes is this wedge of the pie, and so on. This is one earthquake in 1960, the magnitude 9.2 Chile earthquake. This is the Good Friday earthquake in Alaska. This is Sumatra, and this is the recent Japan earthquake. So you can take these 4 earthquakes that lasted in sum total about 18 minutes, and that's 50% of the energy that's been released in pretty much all of the plate boundaries on the planet right there. So these are, again, hugely devastating events. Another way to sort of put this in perspective, I realize not everybody thinks about earthquakes all the time, and so comparing one earthquake to another might not give you a great sense for how much energy is released. So this is just a plot that shows energy in general, and it's a log scale, so each numbered tick mark is 100 times more energy. And this is, well, don't worry about this axis, it's the equivalent earthquake size if you were thinking it was an earthquake. Here's a lightning bolt. Here's Hiroshima here. Mount St. Helens eruption here. Here's a hurricane, your typical hurricane, like a Category 3 hurricane. The biggest earthquake that ever happened in the continental US was in 1812, the New Madrid earthquake in Mississippi. It actually caused the Mississippi River to run backward. There's a great Uncle Tupelo song about that, in fact. And here we are with the magnitude 9 events. This is the Chile earthquake here, Alaska Good Friday, and the Japan earthquake of a few months ago would be just below that here. But these are events where we're talking about energy releases that are on order of 2 weeks to a month's worth of the entire US energy consumption in a year. So it's a huge amount of energy. I'm sorry, I missaid that. It's equivalent to 2 weeks to 1 month's worth of the entire US's energy consumption. So it's a huge amount of energy release. Another way to put this in perspective is to think about the area that breaks in these mega events, in these magnitude 9 events. And so being from Pennsylvania, this slide has meaning for me. If you substituted Oregon, it would be a little bit bigger, I suppose. But the same idea applies, is that the region of the fault zone or of the subduction zone that breaks in these major events is something in the neighborhood of the size of Pennsylvania. And the final way, if you don't like that way of thinking about it, you can think about looking down on the fault zone, looking down on the plate boundary, the patch that broke, how big was it? Again, this translates pretty much directly into how big an earthquake is going to be. So this is what we think of when people talk about the big one in San Francisco, the big one in California. This is the almost magnitude 8 earthquake, like the 1906 event that destroyed San Francisco. This is the Chile earthquake in 2010 that many of you may have heard about it in the news for a day or so, and then people stopped paying attention. This is the recent earthquake in Japan. Down here is the Haiti earthquake, which caused massive devastation for other reasons, mainly because the infrastructure wasn't really there to handle the ground shaking. But again, you get a sense for the relative scales of energy that's released in these events. And this is why we're trying to study subduction zones, is these really are the giants of the earthquake world. And one of the other things that happens in a subduction zone earthquake, you may or may not have even stumbled across some of the examples of this when you go out on the beach at, say, Sunset or Bandon Marsh. But during the interseismic period between earthquakes, things are locked up, and as a result, you're sort of scrunching up the overriding plate by a continued motion of the downgoing or subducting plate. And that causes uplift near the coastline. Well, when that fault suddenly releases and the earthquake happens, hundreds to thousands of years of this uplift that's allowed things like trees to grow on that land, if it's above sea level, suddenly subsides in the neighborhood of 6 to 12 feet. Well, when that happens, and I had the privilege today of getting a private field trip with Ron to see some of these features, this is from 300 years ago. This is what people think is a magnitude 9 earthquake that happened around here 300 years ago, and this is from 1200 approximately years ago. You see basically the roots of trees that died because their roots were submerged in salt water going from here to here. And so there's not just tsunamis that are generated when this kicks out here and bumps up the seafloor and displaces water, but you can also have coastal damages associated with subsidence. All right. So in terms of drilling, what are we trying to do or trying to understand about earthquakes, and how can we use drilling to get at that? Well, there are a couple of fundamental things we don't really understand about earthquakes, and I'll show you a couple of examples of that. And then I'll launch into showing you some of the key things we've found so far from our drilling program into these plate boundary systems. So one thing that we know is that, well, earthquakes happen only in particular regions. When an earthquake happens, for example, the massive 1960 earthquake offshore Chile, it didn't break all the way along the entire South American margin. It only broke a segment of that. Well, why is that? What controls why earthquakes start and stop where they do? We don't know. Presumably, it has something to do with the conditions at depth along the plate boundary, maybe the properties of the rocks along the plate boundary that cause it to be sort of a barrier. So as this earthquake starts breaking through, something causes it to sort of stop or be unable to nudge through and continue unzipping. Now what we're looking at is overlaying on the locations of these earthquakes. This is from the 2010 magnitude 8.8 earthquake in Chile from February of last year. This is a map looking down on the fault surface of the plate boundary showing the distribution of slip. And you can see that in some places, these blue colors, the colder colors, slip was in the neighborhood of maybe 1 meter. But then there are other places along the plate boundary that slipped upwards of 10 meters or upwards of 30 or so feet. And so why is it that some areas slipped much more than others? Well, we don't know. But again, presumably it has something to do with the rock properties and the conditions in the subsurface. And if we can actually drill into this and sample it, we might have some great insight into what it is along these plate boundaries that allows lots of slip, which could in turn generate tsunamis here versus not so much slip, for example, down here. And just as another example of that, this is a map showing the slip distribution for the earthquake offshore Japan. And again, the idea is that if you can access these areas where there is extremely high slip by drilling into them and sampling the rocks and making measurements down in the earth, we can learn a lot about the conditions and the properties of the rocks that may allow such high slip in particular regions. Now, in the case of the Japanese earthquake, what's remarkable is that the amount of slip that happened all the way up right to the trench, so basically right to that area, like in that first slide where I showed you that little carbonate crust, over 60 meters, so 200 feet plus of motion of the top plate relative to the bottom plate. I mean, that's actually kind of a record in a sense. It's the highest amount ever seen. It's in part what's probably responsible for the size and timing of the tsunami that hit Japan, is that the slip happened very shallow, and also that it happened where it did actually was good because that gave more time before the tsunami hit compared with that slip happening somewhere closer to shore. And so again, the timing of that tsunami is partly related to where it slipped. The size of the tsunami is partly related to the fact that very shallow slip on the fault is a very efficient way to bump the seafloor and cause a tsunami. I should mention one other thing here is that one thing the ocean drilling program is actually starting to investigate as we speak is the possibility of what we call rapid response drilling. So drilling into the zone, because it's so shallow, it's very accessible by drilling without getting too deeply. If you drilled 1 kilometer or 1.5 kilometers down, one could reach this zone of very high slip and see what does a fault look like? What's the fingerprint of an earthquake that just slipped 60 meters? It's something that's never been done. And we'd learn a great deal about earthquake physics if we could get in there soon. And so this is something that may happen in the next year. All right, and then the final thing, I mentioned this not a few slides back, is the seafloor uplift that causes tsunamis is greatly influenced by whether the earthquake breaks along a splay fault, as we call them, like this branch fault here, and bumps up the seafloor here, versus propagating to the trench, as we think it did in the Japan earthquake, and bumping up the seafloor here, versus doing neither and having sort of buried slip that peters out in the subsurface. Each of those would have a very different, both a different size of the earthquake and, more importantly, a different timing and size of a tsunami. And so trying to understand the role of these splay faults versus the master plate boundary, or what we call décollement zone, is also of critical importance to understand tsunami and earthquake risk. And the final thing I'll mention here, mainly because it's very relevant to Cascadia, to the subduction zone that we're sitting above right now, is some of the weird slow earthquake and strange slip behaviors were first identified. The first ever identification and sort of type locality for these is actually here in northern Washington. And so these kind of weird slow slip events at the down dip, deep edge, and the shallow edge of the system, well, what causes those? And again, are they somehow linked to triggering major mega earthquakes? Well, drilling into zones, at least in the shallow part of the system where these weird slow earthquakes happen, would allow us to understand them better as well. Now, one of the things that people always ask me is say, well, Demian, fine, you need to understand earthquakes, but why can't you just go to the seafloor? Here's the trench, right? This is that picture I showed you before. This is a zoom in with the robot claw of the submarine, taking a sample of this carbonate here. So it's actually about 50 centimeters high. It's not that as tiny as it looks here. And this is the submarine. It holds 2 people and a pilot in a titanium sphere about 6 feet across. It's a wonderful adventure if you have a chance to go in it. Just don't drink too much coffee before you go. There is no restroom. So we can look at the seafloor. Now, the other thing we can do is we can look at rocks that have been buried and then geologically uplifted. So we can think of these as dead or extinct seismogenic zones. For example, in Kodiak, Alaska, there are rocks that have been brought up from 15 kilometers down. They were once in the heart of the earthquake generating zone, and now they've been uplifted for us to look at. The same is true offshore Japan here. This is Steve Hickman for scale. So this is all well and good. We can certainly learn a lot from looking at these extinct systems, but the analogy that I like to use is that it's kind of like studying the human body. So here, sure, we can look at somebody's face and see that they breathe every once in a while and stuff comes out, and we could go to the morgue. But that doesn't really tell us much about how the human body works. So in order to understand what's happening, we really need to get into and sample and monitor the living, breathing system. And this is where drilling is not just important, it's actually essential. And the combination of strategy we use is sampling at a variety of different depths to do the equivalent of biopsies, to see what's down there, how it behaves, and make spot measurements of the materials and their properties, but then also to hook it up to a monitoring system, to an EKG, and continuously monitor in boreholes to listen for mini earthquakes, micro earthquakes, to measure the conditions of fluids and temperature and how they vary over time in between earthquakes and after small, medium, and large earthquakes. So I'll show you a little bit of each of these things that we've done offshore Japan as examples for how we're tackling this problem. So the study area is offshore southwestern Japan. So just to kind of orient you, here's Japanese islands here. This is the main island Honshu. Here's Tokyo Bay here. This is the Nanchi Trough, or southwestern Japan. Northern Japan here, the major earthquake from March occurred up here off of Tohoku in northern Japan. And the study area for us for this project is off of the Key Peninsula here. We call the Key Kumano transect. And I'll show you a zoom-in map here in just a minute. Sorry. A zoom-in map here in just a minute that shows you in more detail why we're drilling there and where our drill sites are. But first, just another sort of quick thing is, why do we go to Japan? Well, the easy answer is, well, the drill ship was built by Japan. They paid for it, so we're going to go drill offshore Japan because it's a matter of national interest. And I'd be lying if I said that wasn't part of the answer. But a big part of the answer is also that the science is very well defined there. And so we have a place because of a tremendous historical and written record, 1,300-year record, where there's no detective work required. It's a written history of major earthquakes, magnitude 8 or greater, what we call great earthquakes, along this margin. And this is shown here. Some of them break only sections of it. Some of them break all the way across the entire margin, and others break other sections of it. But it's very well documented in terms of the ground shaking and where tsunamis hit and how big they were. So that's a big part of it. A big part of it is that it's within just the geometry of the subduction zone means that we can actually drill with the capabilities of the drill ship and get to the plate boundary. And that's not true everywhere. And then, of course, there's a huge investment onshore in monitoring that we can tie into from the offshore to basically monitor the entire system from top to bottom. So the area where we're working, this is again zoomed in off of the Key Peninsula here, off of Honshu, is directly above the zone where the last major great earthquake that affected Tokyo occurred. This is 1944 Tonankai earthquake. And so that's shown in map view here. Here's the Key Peninsula. Tokyo is kind of just off the map to the north here. These black contours show the slip distribution. And unfortunately, I'm sorry, they're not labeled here, but each contour is 1 meter worth of slip. And so the fault slip or plate boundary moved up to 7 meters or about 23 feet in this zone here, and then it kind of peters out on the edges. But in this event that happened 65 years ago or so, we can actually drill into the upper edge of this in a place where it slipped 10 or 15 feet and actually learn something about the fault rocks there. So that's the zone of slip in that great earthquake. There's also some of these funky slow events, what we call slow earthquakes or very low frequency earthquakes. A swarm of them popped off below but in the mapped region of this red box in 2003, 2004. And so this was kind of after we already planned the project, but it's sort of a bonus. It actually means that not only can we drill to penetrate the fault zone, the plate boundary that broke in the last great earthquake, but we can also drill some holes in this region and understand what's happening above and within this sort of weird zone that slips in slow earthquakes. And then the drilling sites are arranged in a transect going from shallowest to deepest penetration to get into the fault zone or across the plate boundary at these series of red and green borehole locations. And this is kind of showing you in a 3D block diagram what that looks like. So the aim of the Nanosize project is sort of multifold and multi-stage. What's shown here is that this is a seismic reflection, or basically acoustic image of the subduction zone here. The scale here is about 150 kilometers and 10 kilometers depth-wise. This is the sea floor here. You can see the trench is located right about here. So this is the Pacific plate here, or actually the Philippine Sea plate here and the Eurasian plate here. So this is the true plate boundary that you're looking down on in Google Maps. And a series of boreholes in this transect. The first stage of this was to sample what we call the subduction inputs. So this is the stuff that's riding in on the subducting plate on this conveyor belt, and eventually it ends up down here and becomes the material lining the fault zone where earthquakes happen. The second stage is to penetrate these branch faults, the main plate boundary and branch faults at shallow depths to understand their properties. Sorry. To understand their properties, and in particular to try to understand a little bit about whether they break in earthquakes or not. Of course, if they do, that has profound implications for whether tsunamis will be generated and how efficiently that process may work. The big sort of capstone of this project is riser deep drilling to 6.2 kilometers below the seabed, and here you're 2 kilometers below the ocean surface, which is here, to drill into the plate boundary where earthquakes actually slip and nucleate. And that's slated for 2012 to begin that drilling, and probably we'll get in 6 months of drilling straight, we'll probably get to about here. And then we'd come back in 2013 and finish the job. And of course, the final piece of this is the listening part. Beyond doing the biopsies, you want to monitor. And so we'll do what we call wiring the megathrust. And this would be continuous monitoring, instruments that are recording signals every second or every minute in boreholes spanning across this upper edge of the seismogenic zone. So some of the key results that I want to tell you about. First, I'll talk a little bit about some of the measurements we've been able to make in boreholes and what we've learned about the conditions down there along the plate boundary where earthquakes either are happening or for some reason maybe aren't happening in particular places. I'll then tell you a little bit about some of the things we can do by torturing rocks in the laboratory when we get them back from the drilling and coring, and how those tell us about earthquake processes. And then finally, I'll tell you a little bit about some of the very recently installed borehole instruments and monitoring systems that we're using to essentially take the pulse of this system. So one of the key things that we've learned, now this is a zoom in on one of these seismic reflection or acoustic images near the toe or the tip of the subduction zone, and just the anatomy of this thing. So this is the incoming or subducting plate here. So it's moving this way through subduction, converging with the upper plate here. The boundary between those two plates is actually very clearly imaged here. So right here is what we call the décollement, or plate boundary. Everything above it is being plastered onto the upper plate, the upper tectonic plate, kind of like snow or sand in front of the blade of a bulldozer or a snowplow. And everything beneath it is bypassing that and going down with the downgoing or subducting plate. So here you are, this is your plate boundary. In boreholes that sample the outer reaches of this system, so from the trench near the toe of the system back a few tens of kilometers, one of the things that we've observed is that the fluids that are originally contained in the space and the sediments, so you think of this as like mud, it's got a bunch of water, seawater in the space between the mud particles. As that gets buried, those fluids get trapped and pressurized. And you're actually forming the equivalent of a kind of a cushion of fluids that lines the boundary between the upper plate and the downgoing plate. And not only are we able to get at this through drilling boreholes and making measurements in the boreholes, but we're also able to connect that with very high quality acoustic imaging to basically map that property around within this sort of layer of sediments that lines the plate boundary. So what I'm going to show you next are a series of slices taken out of images like this one, where we can actually map the stiffness of the rock and the properties of the rock, essentially the water content of the rock, using the acoustic imaging. So this is sort of akin to a CAT scan, but not quite as high a resolution. So what you're looking at are a series of slices, and I'm going to go back for a second. Each of these slices is basically a slice or a slab at different depths, from here, 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 and here, but all within this layer that's lining the plate boundary. So this is the topmost layer. The trench is here, and this is 20 kilometers or about 13 miles back from the trench. This is a little bit deeper still, and a little bit deeper still. And what we're actually able to do is map the fluid content from very fluid rich in blue to a little bit less trapped fluid in red, and quantify from the amount of trapped fluid, say something about how high the pressure is in that fluid that's acting as a cushion or sort of floating things, and lubricating the fault system. So the analogy that I like to use here is, if anybody here has ever played air hockey, what allows that puck to glide easily is that there's very low frictional force acting on that puck. It can glide because there's not much connection between that and the table. Well, that's because you're pressurizing it with air. Here we don't use air, but nature uses water, does the same thing. So that trapped fluid is this sort of cushion that allows things to move without much stress. And the result of those studies, that work, is basically that the outer reaches, the outer 20 to 30, maybe more, kilometers of this system, from the trench back almost all the way to where this branch splay fault comes up, is highly overpressured, meaning that the fluids are trapped here. And we think that this offers a really nice explanation for why we don't have earthquakes popping off here. So this outer region is typically thought of as being aseismic. Earthquakes don't start here. They certainly don't nucleate. Typically, it can glide along peacefully, and that would make sense if it's got this sort of cushion of trapped fluids that allows it to glide easily. It can also explain why these fault systems and plate boundaries are mechanically weak. It's something I didn't really talk about before, but it's a conundrum in the world of plate tectonics and earthquake physics, is that plate boundaries seem to be pretty slippery in general. And one way you can do that is if you pressurize the fluids. Now, the other thing that's sort of just come up as an interesting outcome or idea that we can connect to here as well is that we may not be able to create earthquakes here. So they may nucleate somewhere way down the subduction zone down here. But if they unzip and break to this point, well, then suddenly you have a zone of very low resistance from here all the way out to the trench. So events like the Japan earthquake that unzipped and ruptured all the way to the trench with extremely high slip, well, that could happen if you kick this from behind because it's not going to offer much resistance. And so that may also be an explanation for the idea that rupture in big events can make it all the way out to the trench. So a couple of other things that I'll talk about now, not just things we can measure in the boreholes to learn about earthquake processes and the mechanics of these plate boundaries, is what can we learn from essentially torturing the rocks we get back. And so we make a variety of measurements of what we call physical properties of these fault rocks. So here is just an image of some of the core material or core samples in the fault zone. This is actually from offshore Southwest Japan. This is the main plate boundary fault from 1 kilometer depth. And you can see it's kind of busted up, broken up rock with some kind of fabric in it going this way. So this is the fault zone itself. And we make all kinds of measurements of the acoustic properties, magnetic properties, the porosity or compaction state of the rock, the strength of the rock, how easily fluids can move through the rock. And one thing I'm going to talk about in just a second here is the friction of the rock. So it's how easily you can slide things back and forth if this rock is what's in your fault zone or in your plate boundary. And the samples I'll talk to you about come from these shallow fault zone penetrations that I told you about as one of the stages in the Nanchi project. And so we have two regions. One is out near the trench where we drilled through the plate boundary fault, the main plate boundary here, or décollement, and then a drill site that goes through this splay or branch fault, also at a pretty shallow depth. So these are both sampling the rocks at depths of only 500 meters or so. So half a kilometer, a third of a mile, zones where earthquakes are definitely not nucleating, but maybe they do rip through it or propagate through it. And one of the things that we do is we do these friction tests in the laboratory. This is a graduate student, Stefano Mazzoni, who's now, he's sold out to the man, and he now works for Chevron in the Bakersfield area. Don't tell him I said that, because he may give us some money someday. But here he is preparing a sample, and here's our laboratory shearing apparatus. And I'd be happy to answer questions if people have them after the talk. I don't want to go into too much detail here, but it's basically a rock torture device where we can make very precise measurements of the friction and the strength of the rocks. And a couple of the key findings that we have is that these fault zones, maybe not surprisingly, in addition to trapping fluids, the fault zones themselves are lined with minerals or materials that are intrinsically slippery or weaker. Turns out that this is also true, we think, of the San Andreas fault. So it's not a special case for these subduction zone plate boundaries. But what we're looking at here is looking at measurements as a function of depth. This is the friction coefficient. So lower numbers means it's slippery. Higher numbers means that it's harder to slide. And when you get into the fault zones, they are in the neighborhood of 30 to 50% weaker than the surrounding wall rocks. And so the fault zone is not just trapping fluids, but it's also slipperier, just intrinsically so. The other piece of this is we also measure the permeability, or how easily water can flow through the rocks. And we find that the fault zone is less permeable. So these numbers here are measures of permeability, where this is a very tight rock, and this would be a rock that fluid or water could move through easily. The fault rocks are in the neighborhood of 10 to 100 times less permeable than the rocks around them. And this would make sense because this is rock that's been smeared out and smashed and sheared, and so presumably it's more compacted and should be less permeable. But this means that it ought to be very efficient at trapping the fluids. So we have sort of a dual mechanism, slippery material that can also trap fluids. Both of these are going to contribute to a slippery, weak fault zone that should be aseismic in that it can't cause earthquakes, but it's happy to go along for the ride because it's so slippery. And one of the other very interesting things that we've found is that if you look at not just how strong the rock is when you try to slide it, but if you try to slide it faster versus slower, what happens? What we find is that these fault rocks, from these very shallow depths, so again, just to orient you, these shallow depths here and here, when you try to slide them faster and faster, they get stronger. So this is the highest speed, they're very strong. At the lowest speed, they're also pretty strong. And it turns out that they're weakest, so they're most easily slid at these intermediate to slow velocities that are in the neighborhood of 1 to 3 microns per second. Turns out that that rate, where they want to slide most easily, just so happens to match up with the rates that the fault moves when we talk about these weird events like slow earthquakes and slow slip. So there may be a really clear connection between the properties of the rocks and what allows these weird behaviors to happen. And we're just now starting to investigate this more deeply, but it seems like a promising direction. One of the final things I'll say about the core samples before I jump in to tell you a little bit about our monitoring studies taking the pulse of the system is this very, very innovative approach that some of my colleagues in Japan have just started using to try to essentially interrogate the rocks that we get back from the fault zone. So we've drilled these core samples, we take them out, and you want to ask the rocks, if you could, how fast did you slip? Did you ever have an earthquake run through you? If so, how fast? Well, as you might imagine, unless you're like the rock whisperer, like the dog whisperer, that's not an easy thing to divine from looking at the rocks. But there is a really clever technique that's used. And it turns out that even in these fault rocks, these ocean sediments, basically, that have been squeezed and deformed and put into the fault zone, there are little organic particles. Basically, you can think of these as little bits of coal. And if those get heated up for any reason, they change in a way that you can measure. They basically become more crystallized. And so there's this technique called vitrinite reflectance. And the idea is to use the reflectivity or the patterns that you see under a microscope of these small particles of coal. And they actually tell you something. They're like little paleothermometers. And so what these researchers found is that as you go across the fault zones, whether it's this splay fault or the main plate boundary, the décollement near the trench, in both cases, they see an increase in the paleo temperature, but it's localized right in the fault zone. So this fault zone got warm, and the rocks around it didn't. Well, one way you can do that is with friction. And so maybe you guys don't have to do this in the wintertime in Oregon. In Pennsylvania, it's cold enough we do. You want to heat your hands up, and you do this, and it's frictional heating. It's the friction, how hard you're pressing, and also how fast you're moving your hands together that generates that heat. Well, in order to generate the kinds of heat that are recorded in these little organic particles, it turns out you'd have to have basically earthquake slip rates. And so there's some paleoseismicity evidence here that these rocks are recording earthquake slip even at shallow depths. This would be consistent with the idea of kicking this thing from behind and having it along for the ride, but move fast enough to heat stuff up and also generate a tsunami. And so this is, again, a really innovative approach to be able to look at the rocks and say something about whether earthquakes have happened in those rocks. It's really the first time this has been done. This was just published this year. So the last part of this major project, in addition to the drilling the holes, making measurements down the holes to look at the conditions in the earth, and sampling the rocks to torture them in the lab or interrogate them, is to actually put instruments in boreholes and measure what's going on in real time. And so that's what we've done in a couple of boreholes, and I'll just tell you quickly about what we've learned and what we've done so far. So this is that splay or branch fault. So here's the cross-section of the overall system that you've seen a bunch of times now. Here's the seismogenic zone, or what we think is the seismogenic zone, where it's locked up and where earthquakes can nucleate or be triggered. Here's the borehole that I just showed you some of the data from that penetrated across this branch fault, or the splay fault. And if we zoom in on this area here, this is again one of these acoustic images, a seismic reflection image. Here's that splay fault here. We drilled a hole across that fault, and at a depth of about 1/3 of a mile, 500 meters, we installed casing. That casing is about 10 inches across. That basically holds the hole open. And then inside that casing, we have some screens that allow a connection or access to the fault zone itself. And then we installed a series of instruments to measure the fluid pressure and temperature every minute from 2009, when we put these things in, to late 2010. And then we actually just pulled this thing out and put new instruments in and swapped them out. Just for reference, after I show you the installation from this location, I'll also jump over and show you something we recently put in the ground at this location here, which is not penetrating through any fault zones or into the seismogenic zone, but it's in the hanging wall, or the zone just above where we think earthquake slip happens. And so we put some instruments in this hole that I'll show you in a couple slides. But first, in the splay fault, this is the instrument package that we put in. And so this is before it went in. This is the sealing device, or what's called a packer, that actually seals up the borehole so that we're not just measuring the ocean. And then this is the instrument package. Now, it doesn't look so exciting, but embedded in this sort of torpedo hull here is temperature and pressure sensors to monitor what's going on in the fault zone. And it was taking a measurement, a reading, and recording it every minute. Here's what it looks like from the underwater camera as it goes into the wellhead or the borehole. So this is what I was talking about, where you're dangling something that's the equivalent of the width of, say, a human hair or a piece of dental floss from the equivalent of waist height, and trying to hit something that's the equivalent of the head of a pin to get it in the borehole. This is at 2.5 kilometers or 2,500 meters water depth. So, we're talking about well over a mile, almost 2 miles water depth. And then this is showing it got in and is now being run down into the borehole inside that casing to be installed. Now, you may also notice, and this is what it looked like when it came out, a little worse for the wear, a little rustier, but more or less the same stuff. You may notice that it's got some writing on it. And so this is one of the things that, if you go out on the drill ship, if you happen to be the chief scientist, you can do whatever you want. And this was August 21st, 2009. Well, my wedding was August 21st, 2004. So I was away from home on my 5th wedding anniversary. This was not good. But I decided that one thing I could do is, the engineer said, if you want to be able to see this thing to get it in the borehole, you got to paint it with this marine paint that's glow in the dark almost. So I said, well, do I have to paint it a solid color? Can I do whatever I want? And they said, no, you just need to be able to see it. So this says happy, and this says anniversary on the other side. And it got me a lot of points, way more points than flowers or anything. So let's see. All right. So the other borehole installation that we put in, this is now a more complicated borehole installation that we put into that hanging wall. So this is now not through a fault zone, but it's basically listening to the rocks as they maybe creak and groan a little bit in the zone directly above the plate boundary where we think earthquake slip typically happens, and in the zone above where earthquakes may nucleate. And so at this borehole, this is kind of a schematic showing you a very complicated, very ambitious borehole installation. It's a kilometer-deep borehole getting into the upper part of that bulldozed pile of sediments that forms the upper plate. And in this borehole, we installed pore fluid pressure sensors at 2 different levels, and we combined that with temperature sensing, a seismometer, a tilt meter, and a strain meter, so that we can actually monitor over time if the borehole is getting tilted because of strain and stress accumulating in between earthquakes. And the strain meter does the same thing. It senses whether the rock volume is being squeezed around that sensor. So this is many, many instruments that are all tightly integrated, and they all have cables or hydraulic lines that come up to this wellhead. And these are just some photographs kind of giving you a sense for what the individual components look like. Here's the wellhead with the electrical cables from the tilt and the seismometer coming up. The wellhead itself is on the order of 3 meters high, all said and done. It's, by itself, it's a pretty hefty looking piece of equipment. And again, this is running down into the earth, the equivalent of, well, it's a kilometer, so about 2/3 of a mile. And just to show you the kinds of things we're seeing, so that first installation, the happy anniversary plug, as I call it, we were in the earth there recording every minute from August 2009 through November 2010. Well, when we pulled this thing out and we saw that the electronics were still alive and that it worked, we had the first hallelujah moment, it worked. And then we said, well, okay, this is a huge data set, it's every minute for a year and a half. Where do we want to look first? So, well, what was the big thing that happened in that time period? In February of 2010, a magnitude 8.8 earthquake occurred in Chile, across the Pacific Ocean, thousands of kilometers away. Let's look at that time window in our data set, in this case from a borehole offshore Japan, thousands of kilometers away. And sure enough, so what we're looking at here are pressure. So this is time versus pressure here. And this data set that I'm showing you, the plot shows a few days worth of data. And so the green curve shows you the tide that we measured. It's just the tides of the ocean. So this is actually just the pressure at the top of the system. So it's the ocean pressure. And it's going up and down because of the tides going up and down. And this is the pressure of water in the formation. And you can see 2 things here. One, the pressure in the formation is a little bit higher than the surrounding ocean. So this is what I was telling you before. It's slightly overpressured, or the fluids are trapped, and that's why the red curve is above the green curve. And we also can see in both the formation pressure and in the ocean pressure a few weird events. One of them, it may be a little bit difficult for you to see, those of you in the back, but in addition to this very smoothly varying curve, this kind of wiggling. Well, that wiggling actually corresponds to something. That's the arrival of waves from the Chile earthquake. So that's the actual ground shaking. This is basically a seismometer, but it's measuring the water pressure. And we see it in the ocean water pressure too, because the seafloor was moving up and down with those waves passing. But we see it's stronger in the formation because it's basically a higher fidelity recorder of that signal. It's basically like hitting a rock with a hammer. The signal inside the rock is better than the signal at the edge of the rock. And that's kind of what we're seeing here. And then about 12 hours later, we see this other much larger amplitude signal, both in the seafloor pressure and in the formation. And this is the tsunami that came through from the Chile earthquake. And so this is, more than anything, was just kind of got us excited, not because it tells us anything great about earthquakes, but it shows that these instruments are both incredibly sensitive and working very well. And we're able to see, if we can see big earthquakes that far away, we should sure as heck be able to see small, slow, medium, big, all kinds of things that are happening in our backyard here offshore Japan that are much, much, much closer. And just to give you an example of the kinds of things that I'm talking about, this is a series of sealed boreholes that have been in operation about 200 kilometers away to the southwest offshore Japan. So our drill sites are up here somewhere, and these sites are off of this is Shikoku Island, the one that looks kind of like the Batman symbol. And these 2 boreholes here recorded during one of these slow earthquake swarms. Here's just a bar chart showing basically days during 2003, the activity of these little slow, weird earthquakes in this region. And that's the best we can do, is we can just count them, basically. It's how many of them are happening. But we actually see signals right around the same time triggered in the pressure signals in these boreholes. And so they're actually sensitive indicators of the rock being strained and stressed and creaking and groaning. And we're hopeful that we can learn not just about big normal earthquakes, but also about these slow, strange events and potentially about how things build up between those big events. All right, the final key piece of all of this, in addition to drilling shallow holes or deep holes and putting things in the ground to monitor, is the capability that allows us to drill these very deep holes to access the fault zones where earthquakes nucleate. And again, I mentioned this earlier, this is basically riser-based drilling that allows us to do this. And it's a technique that's been around in the oil patch for a long time, but it is newly available to the scientific community. And when I say newly available, I mean that cruise in 2009 that I was on was the first time we'd ever done it as in the science community, to be able to drill boreholes, keep them more stable with this technique, and drill much more deeply with this new technique, or new to us. And so the key things are it allows a wider range of measurements because you can really control the borehole from collapsing in on you, and you can get deeper for that same reason. And here's just some of the heavy equipment for those of you who like to see these things. So the riser itself, which is what connects the ship down to the seabed and actually allows control of that borehole, is a pipe that's 3 feet across or so, and it actually has a bunch of that 3 feet is actually buoyancy on the pipe itself because it's so big and so heavy that it basically can't hold its own weight, or it would break itself. And so you have to give it some buoyancy to kind of help hold itself up in the water column. And then the blowout preventer, which you've all heard about probably for not so positive reasons, say from the Gulf of Mexico, is designed, it latches on to the top of the well down at the bottom and is designed as a safety measure so that if you do encounter gas pockets or pressurized fluids, they don't come shooting up the drill pipe and destroy the ship and cause damage, but they're actually prevented. The blowout is prevented by the blowout preventer. That's why they call it that. So it's basically a 70,000-ton hunk of steel with that expressly that purpose. And so ultimately the goal and the next sort of journey we're embarking on is to drill this deep borehole using this riser technique. As I mentioned, this will start in 2012, and so that's again the sort of capstone piece here, to drill this borehole to 6.2 kilometers depth in what is about 2 kilometers of water to hit the plate boundary and the branch splay fault. Here's the branch splay and here's the main plate boundary below, to sample the rocks and make measurements at depths where earthquakes actually kick off. And ultimately, the not so distant future, the idea is we already have an observatory here and here, we'll add one in this deep borehole as well, so that we can monitor in sort of an array of locations to document where things are locked up and where they may have the potential to break in the future. And I think I'll leave it there and be happy to answer questions.
So if anybody has a few questions, I'm going to have you use this because we are live streaming it.
Are you aware of the stuff at the Rocky Mountain Arsenal in about the 70s where they injected chemicals?
Oh, yeah.
Okay. Second thing, do you have chemistry in that probe?
I'm sorry.
Chemistry?
Chemistry? In the probe. You mean in the observatories? In the first generation that we put in, it was just pressure sensors and temperature. When we replaced it, we actually replaced it with those same instruments, but we added a module to sample the fluids. And so those fluids will come back, and we'll have a time series, excuse me, of those fluids as they're pulled out of the borehole and can measure the chemistry. No, actually only in the very shallowest part of the system where it's in contact with seawater and still is oxygenated, at least a little bit. So it's once you get below the sulfate reduction zone, 10 meters or so, there's none to speak of. And for those who don't know, the Rocky Mountain Arsenal was in the 60s. They were injecting wastewater and triggering earthquakes, and that's how they were caught, was monitoring of what they thought were explosions, and it turns out they're, yeah, hydrofracking, exactly.
Yeah, I have a very basic question about this part of the world. In the diagrams I've seen, particularly like a New Scientist magazine about the earthquake, they show the ocean plate being the Pacific plate, and then they show Japan being on what they label as the North American plate.
Yes.
Is that correct?
Technically, it is correct, yeah. I don't know if it shows it very well. I only have one slide here that kind of shows the whole Earth. But so it's maybe hard to see here, but Japan sits right in this sort of weird, so here's Japan here, it's covered by all the dots which are earthquakes, so it's kind of hard to make out. But the difference between the Nanchi Trough, which is where we're working, and the northern Japan region, which is where the major earthquake happened earlier this spring, is that there are different plates going down. And so it is, in fact, the Pacific plate here that's going down beneath northern Japan, and it's the Philippine Sea plate that's going down beneath southern Japan. So that's perfectly right. And then there's actually quite a bit of debate in the plate tectonics community about the nomenclature of things. But northern Japan, technically, sometimes people talk about it being what's called the Amurian plate, which is a microplate somewhere sitting in here that's not the Eurasian plate and not the North American plate. And others actually have more recently argued that it's actually connected to and part of the North American plate. So it's basically the Aleutians continue here, but that plate kind of scoops down and includes something like this. And so that's actually, I don't want to say it's absolutely correct, but there's one school that does think that that's the case.
Do you foresee this technology leading in the foreseeable future to actually predicting earthquakes to any degree of accuracy?
Good question. As scientists, we hate the P word. It depends what you mean by prediction. What I always like to say is, I think in the sense of being able to better predict where and how big, and in a general sense when, meaning sometime in the next 10 to 20 years versus hundreds of years, I think all of those things we have a great potential to understand. I think if you're talking about precursory phenomena, predicting something for tomorrow, or for next Wednesday, or for May 21st or October 21st, if you believe those kinds of things, I'd hesitate to say. I think that's probably pretty far out there, whether there are precursory signals that would allow that kind of prediction. The other value of a lot of this, and one of the reasons Japan is so heavily investing, is not just to understand the broader kinds of prediction and risk about where and how big, but is actually in terms of early warning. If you have instruments in the offshore region that allow you to sense an earthquake, those signals can go to land through a fiber optic cable at the speed of light, and that may give you 5, 10, 12 extra minutes compared to what you would normally have to be able to say something about a big tsunami coming. And so even though it doesn't seem like a huge amount of extra preparedness, every minute is actually hugely important. And so there's actually a big investment in the sense of what they call early warning, even if it is just a matter of seconds to minutes.
So once again, I'd like to thank all of you. I'd like to thank ORC, the college, the guys in the booth that have provided the live stream, and potentially an archived shot of this if you know anybody that wasn't able to make it here tonight. And also especially to Demian and the Consortium for Ocean Leadership for providing the opportunity for him to travel cross-country and speak to us this evening. So